Even though pretty much every physics book will split these things into two chapters, interference and diffraction are really essentially the same idea. And that is that light will spread out when you confine it, and that then the waves will combine to produce constructive and destructive interference. We can imagine waves in the ocean. Let's say we saw them coming in very uniformly like this, and they hit a breakwater, sort of a pier in the ocean. We know that the waves that get through here won't keep these sharp edges. What they'll really do, by Huygens' principle, we know that each point on this little short wave front will act like a circular radiator, and what we'll get outside will really be semicircles. And this picture from the other physics book shows that. You can see the semicircles here. The spread of the waves after they go through an obstruction is called diffraction, and you can demonstrate this yourself if you hold your hand up to a light and look at the tiny gaps between your fingers, assuming they're not actually touching. You'll see bands of light and dark, and that's caused by diffraction, and it happens because the gaps in your fingers are not gigantic on the scale of the wavelength of light. This is the reason you can hear people talking around a corner or out in the hall through a doorway, because the wavelength of sound when people are talking for speech, it's somewhere around tens of centimeters, and that's also about the size of the doorway, so the sound can bend around corners and into doorways. You can't see around corners because those wavelengths are much, much, much smaller than the size of the obstacles. When light goes through a small slit like this, the result is a lot like what we got from the double slit interference pattern. And one way to imagine that is to say, let's imagine the single slit is really two slits side by side with no gap between them. If the single slit has a width d, we could imagine these two little slits, which each have width d over 2. We can look at every point on the top imaginary slit, and it's matched by a point directly below it on the lower slit. So each one has a partner. The very top of the top slit is matched by the very top of the bottom slit. The bottom of the top slit is matched by the bottom of the bottom slit, and they're all d over 2 away from each other. So what we're going to see, we get the interference pattern we would get if we had two slits d over 2 away from each other. And we can use this to find the points where we get destructive interference. So, for example, if we have a path difference of d over 2 sine theta, we'll get a dark spot when that path difference is 1/2 of a wavelength. So I could rewrite this, I could multiply by 2 on both sides and say, all right, if d sine theta equals lambda, we get a dark spot. What about if we broke it into 4 pieces, 4 slits? Again, each one would have a partner 1/4 of d away, and those partners could cancel each other out. So we'd have d over 4 sine theta equals lambda over 2, giving us destructive interference. We could do a little algebra and write that as d sine theta equals 2 lambda. And you might think, why not do 3 slits that are 1/3 of the distance long? And the reason is there, each slit does not have a partner, and we don't get cancellation. So we only get this for even numbers of slits. If we had 6 slits of length d over 6, we'd get d over 6 sine theta equals lambda over 2 for a dark spot, or d sine theta equals 3 lambda. So if we go back and look at this, we're starting to see a pattern. D sine theta equals lambda, or 2 lambda, or 3 lambda. The pattern is pretty clearly d sine theta equals m lambda gives you the dark spots. Now, why can't we find the bright spots halfway between these points? It turns out that the function that we're really modeling here is more complicated than that, and you can check out a calc-based physics book and it will show you, but we're not going to use it. We'll just look at the dark spots, and we know that the bright spots are somewhere in between. So there's a bright spot somewhere in between these two values of theta that we would get here, but we don't know exactly where from the math that we have. The key feature here is that the spreading is smaller and smaller as the opening gets larger. So this is what we expect. If you open the curtains in front of a window facing the sun, you don't see this spreading. The window is huge compared to the wavelength of light. The bright image of the window on the opposite wall is going to be exactly the same size as the window. There's not really going to be any spreading and certainly not any dark spots because the window width is huge compared to lambda. If we put a bunch of slits together, we get a diffraction grating. What this does is it acts like a prism, and it can split light into its component pieces, and we can make it much more cheaply than we could even make a prism, which is just a cheap piece of glass or plastic. One example of this is a CD or a DVD. There are tiny, tiny little grooves in it that are not huge on the scale of the wavelength of light, and this is what lets you, point it at the sun and you get rainbows reflecting off of it that you can point around the room. It's because it's a diffraction grating.